Leone. Or I'm sorry, yeah. Leone, what's up? No, it's like the solving problems. (16 through 42). That's good? Okay. All right. So let's start with looking at the review. Stop talking, please. Okay. Let's stop talking, please. Let's start by looking at the review. Do we have questions from the review? We'll start there, and then we'll move on to open the floor to other places that there may be questions from. Brock. To be or not to be? That's a question right there. All right, Brockton, looking at to be. Which side did you want to start on? The right. Did it really matter? No. If I look at these two sides, are they basically the same? Yeah, because you just stop talking, please. Specifically, ladies in the back. I'm not looking at you. All right. Brockton, you said starting on the right? All right. Well, first thing we should do is, if you did this thing first, it was easy after that. Greatest common factor is secant squared. If you did that first, you probably got this to work out. Because if you did that first, you would notice that secant squared t minus 1 is something on our sheet. It's tangent squared. And what is secant squared on our sheet? About tangent squared plus 1. And then if we distribute, we're done. Whoa! P3? Yeah. Yep. Every day I do. Maya. 2A. Oh, Brockton, you good with this? Did you want to see it done a different way? Are you sure? Okay. So again, as we're doing these, stop talking, please. If there is question about what I did, or if you could have done something differently, or what if I did something differently, or what if we try it like this, or any of those sorts of things, please stop me and ask. Because obviously there's lots of ways to do these problems, right? And doing it the way that I see is obvious, while nice and informative and a good example, maybe not what you need. And if you want to ask some other, like, hey, what if we tried doing this? How does it work? That's fine. I'm happy to do that. Just tell me, okay? Maya, you said you wanted to look at 2A. Which side did you work on? The left side. Great. What did you do first? It's already in a factored form. Do you mean FOIL? Yeah. So what Maya says is that cosine minus sine quantity squared is the same thing as cosine minus sine times cosine minus sine. And when we FOIL this out, we get that. Great. It's exactly what I would do as the first step. Everybody happy? Notice I didn't show the foiling out, I just showed the result from the FOIL. If you have to FOIL it out by hand, that's fine. I chose not to do that. I would not require you to do that either, but if you did do it, it's fine. What do we see here? I say sine squared plus cosine squared. And guess what? It's done now. Whoa! Not too bad. Is the answer 3? That's a box that's filled in. That's the symbol that we put at the end of our proof to show that we're finished. Jacob, did you have your hand up? Okay. Benny. Which one? 3C. All right. Which side did you want to work on here? The left side, you mean? Okay. I would have done the other side, and I'll tell you why afterwards, but we'll use the right-hand side since that's what you want to do. Here's the problem. To get the right-hand side to work out requires kind of something sneaky to do. Involves these. I'm going to rewrite 1 as sine squared plus cosine squared. And that's rough. Sine squared plus cosine squared. Yep. Not an obvious thing to do, right? At some point, you're going to have to do that if you elected to work on the left-hand side. If you worked on the right-hand side, you can avoid that. But we're doing it to what you asked, so that's what we're going to do. Now, if I look at the numerator, this looks like a quadratic to me. So this looks like the quadratic y squared plus 2yz plus z squared, where y is sine x and z is cosine x. You guys kind of see that? That factors is y plus z times y plus z. So we have cosine x plus sine x minus cosine x plus sine x. In the denominator, I'm just going to combine like terms. Okay there. Look at the denominator. What do you see? It's not 1 or negative 1. Negative 1, you'd need the cosine squared to be negative. Also, to be positive 1, the sine squared would have to be positive. That's something that's factorable. That's a difference of 2 squares. It's like x squared minus y squared, right? So I'm going to factor that. Bless you. You're welcome. And then I can reduce. And there's my answer, right? That was rough. There was a lot of factoring there, right? Including that tricky step of rewriting the 1s as sine squareds plus cosine squareds. Not obvious through most of that, right? Here's my hint to you guys why I thought to turn that 1 into sine squared plus cosine squared. It's that. That's why I did that. How's that 2 going to get there? It's part of foiling something out. So I thought immediately to say, okay, I need to make a quadratic in the numerator. The way I can do that is by replacing the 1 with a sine squared plus cosine squared. That'll get me something quadratic in the numerator that I can factor. So that's what I saw, thinking to do that. But that's not the side I would have worked on. I would have worked on the right-hand side. Now, for the same reason, because of that 2 that I'm trying to get to, I want to turn the numerator into a quadratic. So, I'm just going to multiply the top and bottom by cosine x plus sine x. That's the only tricky part to the doing it if you're starting on the right-hand side. Colette? Okay, so if I do that, then I'd have a difference of 2 squares in the numerator, and I wouldn't get any null term out of it. That's why I chose to do the plus. Does that make sense? Okay. I think that if you had tried that and you got that, you would have been like, oh, can't do it. You'd end up with the reciprocal if you worked it all the way through. And hopefully you'd have gone back and been like, I just need to do the other one. But that's a good question, Colette. All right. So now, when I FOIL out the numerator, and when I FOIL out the denominator, I get this. In the numerator, I see 1. That locks the numerator to be exactly what I need it to be. In the denominator, I see no signs in my denominator on the left-hand side. Right? No signs. So I'm going to rewrite sine squared as 1 minus cosine squared. And when I combine the terms, I distribute the negative, and the cosine squareds get added together, and this 1 is now negative, and I'm at my final answer. I think that's a little bit easier through to the end because you don't have to do any factoring. It's just foiling. Typically, foiling is going to be easier than factoring. So that's why I would have worked on the right-hand side, because I saw, okay, I'm just going to have to FOIL some stuff out. That's not so bad if I just have to pick the right thing to multiply to the top and bottom. As Colette pointed out, there are really only two options. You're either using cosine plus sine or cosine minus sine. If you pick the wrong thing, you would have seen it probably right away when you multiply the numerator out, in which case you can go back and try the other one. Juliana? 4B? Ah, okay. Which side did you want to work on, Juliana? Colette? Sure. The right side, okay. What did you do first on the right-hand side? Good. Then you should have gotten the right answer. Because you're almost there. What's 1 minus sine squared? Cosine squared. And cosine squared times cosine is? Cosine cubed, and we're done. You know how to do this one. You silly goose. And this is a nice one to point out that, like, how much you can kind of glean by looking at both sides of the equation at the same time. So, like, I can see right away that the cosine at the end I'm never going to do anything with, because I still need to have a times cosine at the end. And once I take that sine cubed out, and I have the cosine here, I know that this part in the middle has to give me some more cosines, right? In fact, it has to give me cosine squared. So, like, even if I didn't recognize that right away as one of those Pythagoreans, if I looked a little bit at the left-hand side of where I was trying to get to, it would have been clear at that point that that somehow has to give me cosine squared. I go to my sheet and hopefully would have recognized it at that point. Benny? Yes? Okay, who's up next? Are we done on the review? Okay, we can be. Do you guys have other questions from the homeworks or worksheets or any of these other things? Remember, there are several questions on the exam that are not on the review, right? Several types of questions. So I'm happy to talk about those other topics. Just tell me what you want to look at, and I'll look at the heck out of it, you know? Just waiting on you guys. Guys, remember how to do these kinds of problems? If you don't, you should be able to. I'd love to. Which one? Whatever you want. 2? All right. Here's what I'm even going to do. On number 2, instead of just finding secant, I'm going to just find all 6 of them. Okay? Just for some bonus learning. And the directions for 2 ask us to use identities. So we want to find all 6 exact values. There's 1 down, 5 to go. Right? Because I know cosecant, what do I also know basically for free? Sine. 2 down, 4 to go. Everybody go to that. Now what I'm going to look for is something that relates cotangent and either cosecant or sine together, and just those 2 identities. If I look at my sheet, that would be P2. It says 1 minus cotangent squared is equal to cosecant squared. So, if I try to solve for cotangents, then I'd subtract 1 from both sides. I square root both sides to get plus or minus square root 8. But since I know cotangent is positive, I know I don't have the minus, it's just the plus. And if I simplify that radical, I get that cotangent is 2 root 2. Happy with that. What else do I get basically for free here? Tangent. So tangent is just the reciprocal of cotangent. But I wouldn't write my answer this way. Why not? I don't want to leave the square root in the denominator. Exactly right. So if I multiply the top and bottom by root 2, I get that. 4 down, 2 to go. Everybody good so far? Okay. So now I want to find an identity that relates sine, cosecant, cotangent, tangent, 2 of those to either sine or secant. Seems to me like I can say that, let's say cotangent is equal to cosine over sine. Everybody okay there? If I multiply both sides by negative 1/3, got my answer for cosine. 5 down, 1 to go. Which is the one I still need? Secant. How can I find that? Just the reciprocal of cosine. Do I like that answer? Nope. Let's just rationalize the denominator. And we're done. Got all 6 of them using just identities. Everybody happy there? Is that good review there, Juliana? You're welcome. I'm sorry, what? If I wanted to just find secant, all I would have really needed was this one, and then I could use the alternate version of cotangent that relates secant and cosecant, and then I could do it that way, and can skip some of those intermediate ones. Is that cool, James? You get what I mean? Okay. Who's next? Do you guys have any solving questions? We haven't done any solving ones yet. Actually, you could do a whole boatload of those in the homework. Between 16 to 42 or whatever, and then the separate worksheet. Do you want to talk about any of those? We can still do some more of these guys if you want. That's fine. Also, Leonie. Oh my goodness, I didn't have this one out. I'm not prepared. Give me one moment. All right, which one did you want to see? 14, okay. It's pasting right now, so it's just going to be a second for it to paste. I don't know why it takes so long, but this is what apparently we're doing now with OneNote, so just waiting for that information to paste in here. It's doing stuff, I promise. Here it comes. So I think it was this one. I don't know why it did that. So this one, right? Okay. All right. What I would do here, stop talking please, is I'm going to rewrite everything in terms of sines and cosines. And just to make it a little bit clear exactly what I did, I'm going to draw that original division bar really kind of fat there so it's easy to see exactly what I did. You good with that so far? So I have two fractions that are being divided. To divide fractions, we multiply by the reciprocal. So I have the numerator times the reciprocal of the denominator. And then the same thing for the other fraction. You go to that. And just get one. Yep. Did you try using the Pythagoreans on this? Yeah, it gets real messy if you try going that route. Isn't that disappointing sometimes when you see like something you had like 45 steps for done in like 3 steps? In general, most of these things are not massive amounts of steps. If you start getting up like 8, 9, 10 steps, it's possible you're still moving towards the correct answer, but it might be one of those things like maybe I should go back in square one and think about doing something differently somewhere earlier. Not that you have to, but sometimes you end up just kind of like chasing your own tail a little bit. Yeah. But again, that's like part of the problem here is like developing some intuition, and like you have lots of options of things that you can do, and sometimes it's about making sure you choose kind of the right thing to do to make the problem much easier. And in the beginning, you don't really have any intuition as to what those things are until you've done some problems and like, man, when you have something that looks like this is a bad idea, right? Like the only reason I know not to do a Pythagorean here is because I've done a ton of these and I'm like, that's not going to help me here. It's not, I don't have any secret knowledge. It's just a lot of experience kind of thing. You know what I mean? So part of it is just developing some of that, and it takes time and problems, and doing what you're doing of like trying to do something one way and having it not work out very well, and then trying something new. And then you'll remember, be like, oh, when it looks like this is a bad idea. Because I tried this before, and like bad things happened. You know what I mean? Sometimes it's as much about knowing what not to do as knowing what to do. You're welcome. Who else has some that you want to talk about? If you can't cook up anything else to talk about, we'll just start new things. Does that motivate anyone? Brockton. Of course. Sure. All right. Brockton, what did you want to do first on 1A? Or what side did you look at to do first? Okay, that's fine. Is there a difference here, really? I would say no. In each case, we have one thing, right? We have on the left side, we have a division problem. On the right side, we have a multiplication problem, but it's just like one thing either way. So it doesn't really make a difference, but we can certainly start on the left-hand side if you want. Hopefully the thing that catches your eye on the left-hand side is the numerator. It looks almost like P1, right? But P1 is 1 minus cosine squared. This is cosine squared minus 1. That's not exactly the same. Can we make it exactly the same? Yes. What do we need to do? We can factor out a negative 1. So that's going to make the cosine squared negative and this 1 positive. I'm going to write it that way. Oops, those are alphas. You happy there? And at this point, I'm just going to turn that negative 1 just into a negative sign on the problem. And 1 minus cosine squared is sine squared. Remember, we factored that negative out just so that we could use that Pythagorean. And now if I look at the right-hand side, I want a sine alpha. I have a sine squared alpha. So all I'm going to do is I'm going to just rewrite this as sine alpha over cosine alpha times sine alpha. And now that sine alpha is locked. It's exactly where it needs to be. I'm not going to touch that again. I have the negative sign out front. That's all set. All I need is somehow to turn sine over cosine into tangent. Well, wait a minute. It's exactly what tangent is, isn't it? So we're done. Okay with that, Brock? Yeah, if you didn't take that negative out, it was tough to kind of see your way to the finish line. If you didn't do that, you still were able to get to the right spot. Just as an aside, that's what you would have had to do. And then those cancel out. And it's the same thing as picking up here. Right? You could do that without having to take the negative out. And it still works. Or, probably easier would have been to start on the right-hand side. Yeah, so what I would do is I would be concerned about getting this cosine in the denominator. And I recognize right away I can get a cosine in the denominator by rewriting tangent as sine over cosine. When I multiply that all together, then I get negative sine squared over cosine squared. And then I'll just turn sine squared into 1 minus cosine squared. And then distribute through the negative. And we're done. Does that make sense? Going that way? I think things are just a little bit more obvious what to do going on the right-hand side than the left-hand side. But I don't know that that would have been obvious just by looking at it for most of us. But it goes to show you here for something like this that's essentially like the same thing where you have just like a monomial on one side and a monomial on the other. That if you're like confused at what to do with one side, maybe it's worth just starting over on the other side, right? You know, it's not an unreasonable thing to do. Is that cool, Brock? Okay. So we did that a couple of different ways of going about dealing with that, just to kind of illustrate what was going on. What else you guys want to talk about? Other than gossip that's not related to math, which seems like what most people want to be talking about today. One of these guys. Okay. Do you want to do one of these where we don't use identities and we do use a reference triangle? Okay. Do you have a preference on which one you want to do? Okay. Let's do just say number 3 then. Sound good? All right. First thing I'm going to do is try to figure out what quadrant to draw my triangle in. We know that cosine is positive. What quadrant is cosine positive in? where the x is positive, so the first and fourth quadrants. Then I'm going to worry about where cotangent, oops, I don't want to do that. Let's use green. Where cotangent is negative. Cotangent is negative where the signs on x and y are different. So that's the second and fourth quadrants. So where is my triangle located? In the fourth quadrant. Cosine is adjacent over hypotenuse. And then using the Pythagorean theorem, 16 minus 9, so that's square root 7 for that side. And since it's in the fourth quadrant, and that side is the up and down side, I know that's negative. Good there. And then I can just use my SOHCAHTOA definitions to figure out the values for like sine or tangent or secant or cosecant or whatever. Happy with that? Okay. Should be able to do these problems both ways, using identities or using a reference triangle. I'm not going to tell you which way I'm going to ask you to do it. I might not ask you to do a specific way, or I might ask you to do one of the two ways. Should be able to do it both ways. Okay. Leo. Seven from the solving worksheet. Sure. That's this one, right? That's the same one we're talking about? Okay. So, when I look at number 7, this to me looks like a quadratic. So to solve the quadratic, it's got to be equal to 0. So the first thing I'm going to do is subtract 2 from both sides. And just so we're clear, if y is equal to sine x, this is definitely the quadratic 2y squared plus 3y minus 2, right? How do we solve a quadratic? You could factor it or use the quadratic formula. Does it matter which one you do? Nope. Which way do you want to do it, Leonie? Okay. So this one, we have to do the long factoring because the leading coefficient isn't 1. So we need to find the two numbers that multiply to give me 2 times negative 2. And then add to give me 3. What are those numbers? 4 and negative 1. So what do I do with those? I rewrite the 3y as 4y plus negative 1y. And then make two groups. From the first group, I can take a greatest common factor of 2y. And from the second group, I can take a greatest common factor of negative 1. I notice now that each of these has a y plus 2 in common. When I factor that off, I'm left with 2y minus 1. And then I can set each of these two factors equal to 0 and solve. When I do that, I get y equals negative 2 and y equals 1/2. But I'm not done, because I'm not supposed to be solving for y, I'm supposed to be solving for x. So remember that y is equal to sine x. Oops. So x is the cosine, or I'm sorry, the sine inverse of negative 2. And here x is the sine inverse of 1/2. So I'll go to my unit circle and I'll look for the place where sine is equal to -2. It's not on my unit circle. Well, maybe it's just the value I have to use my calculator to take care of. Nope, it's not. Because what's the domain for sine inverse? It's on your identity sheet. -1 to +1. What are we trying to plug into sine inverse here? -2. What's that give me when I take something outside of the domain and try to do the function to it? It's undefined, right? It's like trying to square root a negative number. Doesn't work. So this piece gives me no solution. We're done with that. This other piece, though, we can do. If we go to our unit circle, we see that sine is equal to 1/2 at pi over 6 and at 5 pi over 6. And since it's asking for all values of x, we have the two solutions, pi over 6 plus 2 pi k, and 5 pi over 6 plus 2 pi k, where k is any integer. Is that okay, Leone? So the factoring was the rough part there. Once we had the factoring done, dealing with the trigonometric part was pretty easy. But the factoring was kind of a ugh. Keep in mind that you could use the quadratic formula there. And that's okay also. Spits out pretty cleanly. You're welcome. Okay, who's next? Okay, well, I guess we'll be done, yes? That's fine with me.